Okay, let's take a closer look at linked lists. Let's consider adding the element Z. Where's the most efficient position to add it? Well, with a linked list, unlike with an array, all we really have is the head node. So if we're going to add a new node, we're going to want to add it to the beginning. And then we're going to want the head, we're going to remove this head link and have it point to our new node. So what that looks like in terms of pseudocode is we want to, assuming we have a new node, we need to set the next of that new node equal to head. And then we're going to set the head equal to the new node. We want to be careful about the order. We actually can't swap that order. The reason is because if we set the head equal to the new node first, then we're losing the link to the head, which we need to set to be the next, right? So here when we're drawing here, we're setting the next equal to the old head, and then we're making the new head. So we can't actually swap them. Now let's consider removing an element. We're going to remove C. So the resulting linked list is going to take the next of B and have it point to D. So what this looks like in pseudocode is that we actually need to get to C, and that actually requires a loop, because unlike an array, we can't just access any element we want on a linked list. We actually need to work through it. And we need two types of nodes to keep track of. So we're going to have a previous node, and then we're going to have another node. Okay, and we're looking for C. Okay, so while node does not equal C, you could actually say this is the node's data, however you want to represent it. We're gonna keep moving through the list. We're gonna update previous to the current node and update node to the next one. So what we're doing every time is we're gonna start at the head, right? First, that's the node. Is that C? Nope. Okay, then we're gonna go on here. And the way we move on here is we update our node variable. That becomes our loop variable that we keep updating. And eventually, okay, we're at C. And so that's where we want to be. We must keep track of previous, though, in addition to the node. So we need two loop variables because we need to update this next there to point to the node after. So as long as the node does not equal null, because it's possible we could search the whole list and it might not exist. So if the node does not equal null, then we are going to we're going to simply say previous.next equals node.next. And so what this is doing is going from B, and it's saying B's next now points to D. I didn't actually remove C, and I don't have to. With linked lists, we're assuming we're in an object-oriented type language, which is going to clean up excess nodes for us when they're not being used anymore. And in fact, Java has something built into memory called the garbage collector that goes through and looks for nodes like C that don't have any references. They don't have any pointers, no links, nothing accesses or uses that data anymore, and it cleans it up. It's one of the reasons why Java is not the fastest language. If you're going to implement linked lists in an older language such as C, then you've got to do all that manually, but that is outside the scope of this course. All right, so let's keep moving on and look into circular and doubly linked lists. So the pseudocode implementation for a linked list would need to change to accommodate a circular linked list. So with a circular linked list, in addition to, we'd have our head, but in addition to head, we would set tail.next equal to head. And as long as we maintain that, it'll always be a circular linked list. With a doubly linked list, that's over here, we actually need every node to not just have data and next, but also previous. If we were in a doubly linked environment, removing our nodes becomes easier. We simply have to loop through and find the node, and then we have access to the previous and the next, right? We would have access to everything we needed. So depending on which type of node and type of list you're dealing with, it may slightly change the implementation of adding or removing nodes. Linked lists can also be implemented using a dictionary or a hash map. So the way we would do that is the data or the node name would become the key, and the value would be node.next. So what does this look like? So imagine you're creating a hash table to represent the linked list we have up above. And so we would say A is pointing to B, B is pointing to C, C is pointing to D, and D is pointing to null. We would probably also want a head. So the head would point to A if we wanted to store that. And down below here, we have an example, some example test cases and function calls with a example linked list class. So this is what, if you sat down and implemented a linked list and then wanted to go use it to store data, this is how it might look.